Hey guys, this is LeetCode with me, coming at you live daily with LeetCode interview prep. Uh, Today I'm going to focus on a problem I got wrong in previous weeks. I was recently discussing this with a friend of mine when we were doing some mock interviews together, trading some mocks, and I thought it was an interesting problem, and I want to talk about one of the solutions here. This is kind of like an extra problem for today because yeah, just want to talk about the solution here. So, sliding window median. The median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value. So the median is the median of the two middle values, blah, blah, blah. You are given an integer array nums in and an integer k. There's a sliding window of size k, which is moving from the very left of the array to the very right. You can only see k numbers in the window each time the sliding window moves right by one position. Return the median array for each window in the original array. Answers within 10 to the negative fifth of the actual value would be accepted. So we have the first three numbers. We need to get the median of them. What the median is the sorted. If we sort these three numbers, which one is in the middle? So we can see negative one would come before one, which would come before three. And so the median would be one. Here in our second window, we have negative three, negative one, and three. So negative one would be our median. Here we have negative three, negative one, and five. Negative one would be our median. So there's a couple different ways of doing this. The first one is to do literally what the problem says, which is essentially from, basically go to index three and we build in this, we take this subset and we literally create a copy of this, these three numbers, and then we sort them, which is k log k, where k is the number of elements in the set, and then we can get the median quite easily. But we're doing a lot of copying. So each number we are copying, each number in our set, we are copying k times. The resulting time complexity is n times k log k. So for each n, we are doing a k log k copy and sort. And so this is not necessarily the most performant way of doing this. There's another way of doing this, which is pretty complicated, and um, it's sort of the way that I solved it. If you've seen like find median for data from data stream, which is another medium hard problem, that one basically is like if we have an incoming set of numbers in a data stream, and we're adding one number each time, and we need to find like the running median. um, then we can use two heaps, and we have basically a heap of our lower half of numbers and our heap of upper half of numbers, and then we can just keep adding to those heaps and then keep them balanced so that one heap always represents the bottom half of the numbers. So we have a max heap that represents the bottom half of the numbers and a min heap that represents the top half of the numbers. But the problem with that is that with this, we actually have to delete elements in our heap once they pass out of our window. And once we delete those elements from the heap, if they are lower down in the heap, they're not the top of the heap. Well, heaps don't provide a really good a way of accessing elements that are lower down the heap. Um, and so the problem with that is that in order to delete elements from the heap, we need to track which ones have been removed from which from the heap, and then essentially we need to do a lazy deletion. So at the time that they do bubble up to one of the top heaps, we can delete them lazily. The problem is also we rely on the size of the heaps to determine which two are at our top to determine if the two heaps are balanced. But the problem is some of the elements in those heaps could also be deleted, and so we would need to track what the real balance is between those two heaps, as opposed to what the size of the heaps is. Um, and so, in any case, I'm sort of simplifying a little bit what the solution is, but those are some of the problems that we encounter in the solution, and it ends up being pretty complicated. So what I want to do here is I want to focus on an implementation of this median sliding window with a balanced uh, binary tree. And in Python, This is a actually have a library called this called sorted containers import sorted list. And the advantage of using a sorted list is that the list is kept sorted. Under the hood, the implementation is a balanced binary search tree. And what that means is that operations to find an element, delete an element, or add an element are O log n. And so what we can do is and uh, and so what we do is we iterate from the left to the right. At each element, we first fill the window, which is filling our sorting list with 3 characters. Then at the next one, or three elements. At the next one, at every index, we add the next index, and we know exactly which number we need to remove. So we add -3, and then we remove -1. And each one of these operations is log n or log k, which is k is the size of our operation. And so our net result is actually better than our naive create the window and sort. We have n log k as our net result. So I'm going to do this. So for first thing I want to do is I want to create my sorted list. So sorted list is equal to sorted list. Then I want to iterate up to k. And then I want to add sorted list and nums of I. And then I want to iterate from in range. I want to iterate from k to len of nums. And then at each step, I want to first, so my old value is nums of I minus k. So this is the value that I need to remove from the set. I'm going to do sorted list dot remove old value. Now, remove will throw a value error if the value is not part of this sorted list. And so that's kind of key. And then I want to do sorted list append nums of I. Great. So now I have a sorted list tracking each position as I iterate throughout my array. And then the last thing that I want to do is I want to have my answer, which is an empty list. And then I want to do ands.append. And then what I need is my median value. And so um, the median is going to be um, sorted list. And we want k divided by 2. So plus sorted list k divided by 2 minus 1. Um, and then we want this divided by 2 if k mod 2 uh, is equal to 0, else we can just do sorted list k mod k of 2. And let's do this as we can refactor this into a get def median just to improve our code cleanliness. Do this return that, but then we do median And then we've iterated through all of our list. Note that we still added one extra value here to the end, and we haven't actually continued our loop to go to the last one. So we just need to append that last number to the end of our answer, and then we can return our answer. So let's try it. Yeah, okay, so we need to add instead of append because we are dealing with a balanced tree. Yep, add. Great. So this worked. Let's try and submit it. Great. So yeah, so we are doing each one of these operations that we're doing is going to be remove is log n, add is log n, um, and we are considering every element in nums, which is sorry, this is log k, and then considering every element in nums, which is O of n. And so this is sort of our elegant solution to this problem using a sorted list in O of n log k time, and then uh, uh, our space complexity is O of k space 12, 11 minutes and 30 seconds. Problem one solved for today. Okay. So I just want to go in and look at this implementation a little bit more. So this is an Apache 2 licensed Python collections library written in pure Python as fast as C. So remove runtime complexity O log n. So this is an important thing to know. Add O log n. That's important to know. We have bisect left and bisect right. So this is really efficient for sorting as well in O log n. Count O log n as well. This is good because we can do, yeah, we can do a bisect left and a bisect right. So yeah, interesting. We have that's a good data structure to know when we're dealing with these types of problems where we need to um, have a removed set of all that stuff. So all of that is good. Oh, and so an interesting thing here is that our indexing is also O of log n. So just to be clear, when we are doing these, this is what I wanted to figure out. So when we're doing these index lookups of our median, each one of these index lookups is O log n, which is okay because we're still doing this just once per iteration of nums. And so, yeah, we might have up to twice per iteration of nums. So we have potentially two log n's here, one log n here, one log n here, and we're doing that n times. So it's n times 3 log k. Uh, and so that simplifies to n log k time and n k space.